Hey everyone. Today we are going to talk about fundamental theorem of algebra. What is fundamental theorem and where do we use it or why do we use it? So the theorem is very simple to understand. It says that any polynomial of degree n has n roots and these n roots can be either real numbers or complex numbers. So yeah, this is the whole theorem, very simple to understand. It's trying to say that if we have a polynomial whose degree is 1, let's say linear polynomial, 2x minus 5 equals to 0, then this linear polynomial will have exactly one root. For linear polynomials, it's very simple to calculate the root. So let's try to find out that root. 2x minus 5 equals to 0. So we will get 2x equals to 5 or x equals to 5 over 2. So for this linear polynomial, the root is super easy to calculate. That is x equals to 5 over 2. We can plot the graph of this polynomial. Let's call it p of x. So the graph is given here. We have a x-axis and the y-axis. And the line in red color is the graph for the polynomial px equals to 2x minus 5. We can see that the graph is intersecting the x-axis at exactly one point. So the point where graph intersects x-axis, that point is called the root of the polynomial equation. Similarly, if we have a quadratic polynomial, so quadratic polynomial is a polynomial which have a term of x square. It can be 2x square, 3x square, and then we can have some terms whose degree of x is less than 2. So we can have 4x, and then we can have a constant term as well. This is a quadratic polynomial. So the fundamental theorem of algebra says that if we have a quadratic polynomial, then that polynomial equation will have exactly two roots. So for example, if we have the polynomial px equals to x square minus 16, then px equals to 0 has exactly two roots. We can draw the graph for this polynomial very simply. It's given here. So we have the graph of this polynomial. The graph is in the pink curve. The graph looks like it's exactly a parabola basically, and we can very easily see that this graph is intersecting the x-axis at 2 points. Here is the first point and here is the second point. So that implies that this quadratic polynomial has exactly two real roots, and we can find out those real roots very easily. Let's calculate those real roots. So we have the polynomial equation x square minus 16 equals to 0. We can factorize the left hand side as x minus 4 multiplied by x plus 4 equals to 0. And when we equate these individual factors to 0, we will get two possible values of x. One is 4 and other is negative 4. So these are the two real roots that we are getting. And corresponding to these two real roots, we have 2 points of intersection of the graph of polynomial with the x-axis. Similarly, we can think of a few more polynomials. So let's say we have another quadratic polynomial. This is x square plus 9. So if we try to find the roots of this polynomial, either we can sketch the graph for this polynomial or we can proceed algebraically. We will do both things. First, let's try to solve this equation algebraically. So I'll equate it to 0 and we will get x square plus 9 equals to 0. You can see that it is not possible to directly factorize the left hand side because it's not coming out to be any kind of formula. So what we will do is we will transfer the constant term to the right hand side and we'll get x square equals to negative 9. Then we can take square root on both sides and we will get x equals to plus minus square root of negative 9. Now this can be written as plus minus square root of 9 multiplied by square root of negative 1. And you should be aware that square root of negative 1 is a very special number. It's called imaginary number iota. It's denoted by I. So we are getting x equals to plus minus square root of 9 is basically 3 plus minus 3 iota. And you can very easily see that we are getting two roots and both roots are purely imaginary numbers. So this implies that we have roots. Obviously, we are supposed to have two roots for a quadratic polynomial, but those roots are coming out to be non-real numbers, and that implies that if we sketch the graph for this polynomial, that graph is never going to intersect the x-axis, and it can be seen very easily by plotting the graph. We have x square plus 9, so we can take the graph of x square, which looks somewhat like this. I'm going to draw the x square in dotted lines, dotted points, somewhat like this. And since we are adding 9 to x square, so we can just take this graph and move this graph upward by 9 units. So we will get something like this. Yeah. So this is the graph of x square plus 9. And we can very easily see that this graph is never going to intersect x-axis. And the reason is the polynomial does not have real roots. Right. Fundamental theorem of algebra says that it doesn't matter if polynomial has real roots or imaginary roots. We don't care about that. What we care is that if it is a quadratic, then it has exactly two roots, which we can see here. And we can have a combination of roots also. It is possible that we have some roots as real numbers and some roots as imaginary numbers. We will see that also. And next we can talk about a higher degree polynomial, cubic polynomial. So for example, let's say we have this cubic polynomial x cube minus x square minus 4x minus 6 equals to 0. So the fundamental theorem says that this cubic polynomial must have three roots. It is up to us if we are able to find out those three roots or not, but it will have three roots. And let's see. So if you solve this cubic polynomial or cubic equation, I have solved it and I figured out that one of the roots is coming out to be x equals to 3. And you can check that out. If you substitute x equals to 3, we will get 3 cubed, which is 27, minus 3 squared, that is 9. Then 3 into 4 is 12, minus 6. So this will come out to be 27 minus 27, which is 0. So x equals to 3 is a root of this cubic polynomial. Similarly, you can try finding out the other two roots, but those roots are not going to come out to be real numbers. And that is visible from the graph of this cubic polynomial. We have the graph here, and you can see that this graph is intersecting the x-axis at only one point, and this intersection corresponds to the real root that we just talked about. Since this graph is not intersecting x-axis at more than one point, that directly implies that this polynomial will have two imaginary roots. And we can find out those two imaginary roots very easily. Let's try to do that. So we have x cube minus x square minus 4x minus 6 equals to 0. And we have established that one of the root is x equals to 3. So that implies that if we try to factorize this cubic polynomial, we will have one factor x minus 3. And the other factor will be quadratic term because this is a cubic polynomial. So we can find out the other factor very easily. If we divide this expression by x minus 3, we will have a term of x square. This will give minus 3x square. We want only minus x square, so we add plus 2x. Then we will get negative 6x, but we want minus 4x. So we can add here plus 2 equals to 0. These are the two factors. X minus 3 will give us one root that we have calculated. The other root can be found out using solving this equation, x square plus 2x plus 2 equals to 0. This is a quadratic. We can solve this equation. X plus 1 whole squared plus 1 equals to 0. That implies x plus 1 squared equals to negative 1. We can take the square root on both sides and we will get x plus 1 equals to plus minus iota. Square root of negative 1, that is iota. So we are getting the other two roots as x equals to negative 1 plus minus iota. And we can see very easily that the other two roots are coming out to be complex numbers, that is non-real roots. And that's why in the graph of this polynomial, we were getting only single point of intersection with the x-axis. So this is basic idea of fundamental theorem of algebra. It says that we have exactly n roots, and those roots can be either real numbers or non-real numbers or a combination of both real and non-real, just like in the last example. So yeah, we can generalize the polynomial as something like this, that we have polynomial p of z equals to z raised to the power n plus a1 into z raised to the power n minus 1 plus up to the last term an equals to 0, where these coefficients can be complex numbers as well. So far we have seen only real coefficients, but coefficients can be complex numbers as well, and still the result holds true that this polynomial equation will have exactly n roots, and those n roots can be real numbers or complex numbers. And before we complete this concept, we'll discuss just a couple of more examples. Let's say we have the equation x raised to the power 5 minus 1 equals to 0. So can we find out the roots of this equation? Answer is yes. It's just the matter of fact that how we are going to try to find out the roots. So one thing is that we can very easily see x equals to 1 is a root of this equation. So we can take out x minus 1 factor, and then when we factorize it, the second factor will be a fourth degree polynomial. So it's going to be a little tricky to find out the roots of this equation. But if you are aware of complex numbers, then the problem becomes a little easier. So I'll just assume that you know complex numbers. If you don't, then don't worry about it. We'll talk about this in another video for sure. So we have x raised to the power 5 equals to 1. And every number is basically a complex number. So this number 1 can be written as e raised to the power I into 0. So this is a Euler's form of representation of complex numbers. Every complex number a plus ib. In fact, instead of a plus ib, let's say, yeah, anything. A plus ib can be written as the magnitude of complex numbers, which is represented by mod z, multiplied by e raised to the power I into theta. This is a complex number. So 1 can be written as e raised to the power I into 0. And we are going to do one more thing, that if we add 2n pi to 0, it really doesn't affect our result. So in general terms, 1 can be written as e raised to the power 2n pi into I. Now we can take fifth root on both sides, and we will get x equals to e raised to the power I 2n pi over 5, where n is the number. N varies from 0 to 5. So n can be 0, 1, 2, 3, 4, not 5. N can take any 5 consecutive integers. We are going to use these 5 consecutive integers. So when you substitute these different values of n, we will get different values of x, and we get total of 5 values of x, because this was supposed to be a fifth degree polynomial. So the first root is coming out to be x1 equals to, when you substitute n equals to 0, this becomes simply e raised to the power I into 0, which is 1, and which was one root. Then we can find out second root by substituting n equals to 1. So when you substitute n equals to 1, the second root will be e raised to the power I 2 pi over 5. And similarly, we can find the other roots. You will see that one root is coming out to be a purely real number, and the other four roots are going to be complex numbers. So this is basic idea of fundamental theorem of algebra. Fundamental theorem of algebra says that if we have nth degree polynomial, and let's say for the sake of simplicity that we have a polynomial in terms of x. So if we have nth degree polynomial px, then this polynomial will have exactly n roots. Exactly n roots. And these roots can be a combination of real numbers and complex numbers. So this is the gist of this theorem. This is a super important theorem, very easy to understand, but very useful as far as solving problems of algebra is concerned. So I hope all of you understood this theorem, and I hope you liked the video. If you did, do not forget to share the video with your friends. And thank you very much for watching. I'll see you around in the next video. Take care. Bye-bye.